Hi there, it took much longer than I expected, but finally, here is the promised second part of the TM4700 appliance safety tester used on a few Class 2 devices. If you recall from Part 1, this old tester uses quite high voltages, and I wondered if modern Class 2 devices could get destroyed as part of a test. But before I start, I want to address some comments regarding my measurements of the Class 2 high voltage in the previous video. As a start, let's see what the output resistance of the high voltage probe is. Slightly more than 1 megohm. I verified that the BM869S has about 10 megohm AC input resistance, which is higher but not that much, so measuring an AC source with 1 meg output resistance will have a loss. About 10% of the voltage will be lost and not seen by the meter, which will therefore read low. Let's see if that is true. The red meter uses the probe, so 1 volt AC means 1000 volt AC. The yellow meter measures the mains voltage from my variac directly. As I increase the voltage, you can see the red meter is indeed low, but far less than expected. 262 volts compared to 264. That's less than 1%, which is acceptable. Why is that? Well, this probe was made for use by multimeters and the manufacturer has trimmed it to deliver accurate readings. Let's measure the input resistance of the probe. This is way more than what the BM869S can read in ohms mode. But not to worry, we have conductance mode, and after a moment to stabilize, we get 1.02 nanosiemens. To convert that into ohms, you have to take the reciprocal value. So the reciprocal of 1.02 times 10 to the power of minus 9 for the nanosiemens delivers about 980.4 megohm. If you do the maths, this value together with a probe output resistance and a parallel input resistance of the multimeter delivers a 1 to 1000 division, so that the meter can be pretty accurate. Of course, if a meter has a much lower AC input resistance, that would not be true anymore. For example, nearly all my bench meters have just 1 megohm input resistance in AC mode. Doing the same test as before, but with a Bryman 869S replaced by a 6.5 digit Agilent 34401A, shows a significant error. Instead of 266 volts, it only reads 140 volts. I should mention here for AC there's the additional problem of input capacitance that will cause a frequency dependent error, but for this application the frequency will always be just 50 Hz, so that can be ignored. The takeaway here is, know your meter specs when selecting which meter to use for a job. A much more accurate and expensive bench meter can deliver worse results. The last thing to investigate is what the output resistance of the Class 2 high voltage in the tester actually is. It turns out that it is about 6.5 megohm regardless of the voltage setting. Since the input resistance of the probe is nearly 1000 megohms, there's nothing to worry about. The loss will be less than 1%. All in all, I think this shows that the voltage measurement in Part 1 were reasonably accurate. With that out of the way, it's time to meet the candidates for today's Class 2 testing. They are plucked from a selection of power supplies that ended up in my recycle bin for one reason or the other. The first is this power supply from a place called MicroTalk. It is supposed to deliver 12 volts 200 milliamps, and it still does when I tested it off camera. It is a Class 2 as shown with the 2 square symbols for double insulated and has markings that claims compliance with German safety standards. Of course, whether that's true is another question. The second candidate is this Philips charger for a shaver that I have since replaced. It is also a Class 2 device and delivers 15 volts DC, but the symbol of 2 overlapping circles means it's actually meant as a current source. I did a quick power up of this one, but rather than current I checked the idle voltage, which was 17 volts DC. Number 3 is this power supply for a battery capacity tester that I don't remember at all. It is marked as a Class 2 device for indoor use and sports only a CE sign, which may signify that it complies with EU health, safety and environmental protection standards, but may also just mean Chinese electronics. Well, so far it still works and delivers 12 volts and a bit, and a blue light is visible on the case. Number 4 is a brand new USB charger, model SPTC78A, still in its box. I have high hopes for that one because of this warning about it by the UK Office for Product Safety and Standards. The warning concerns our SPTC78A model and the risk is a serious electric shock. Apparently 2 kinds of issues. It may come apart when dropped, allowing live parts to be accessed, and insufficient creepage and clearance distances, failing the electrical strength test. Sounds promising. The specs are typical for a 20-watt USB-C charger implementing the power delivery protocol. It can provide 5 volts up to 3 amps, 9 volts up to 2.2 amps, or 12 volts up to 1.67 amps. It has the Class 2 marking and indoor use only, the CE mark and the UK CA mark, which is the UK equivalent of the CE mark. Using a USB power delivery switcher module, the unit is delivering 5 volts. There is of course a significant voltage drop because of the USB-C cable and then through the switcher and finally to the electronic load and the meter, but it delivers 3 amps with no problem, at least in the short time I tested it. Overcurrent happens at 3.1 amp, which is in spec. The same test after switching to 9 volts. It goes beyond the 2.2 amps and only falls at 2.6 amps. Not bad. A similar story after switching to 12 volts. It goes beyond the specified 1.67 amps and falls only at over 2 amps. As far as this short test can determine, this charger is working and meeting or even exceeding its specs. The last candidate is this super lightweight power supply that was included with some Christmas lights I bought from China. I have never used it and the lights are instead powered from an old Raspberry Pi charger. From what I remember, that this is supposedly a 5 volt supply because there's no writing or any marking on this unit. I struggled confirming that this thing still works. There was nothing coming out of the connector. In the end, I just cut the connector off. It will never be used anyway. And yes, the thing actually works. 5.78 volts is quite high, but maybe that is because there is no load. With the candidates all introduced, let's do some testing. Starting with number 1, the MicroTalk 12 volt supply. I already explained that for Class 2 tests, the live and neutral input power pins of the unit under test are connected together. That's already done inside the tester. The only other electrical connection of the unit under test is its output, and so the 2 wires here are also shortened together. High voltage is then applied across the unit between its input and output. Starting with the lowest test voltage and working my way up to the highest, but each time the green light comes on indicating that the unit passes the test without leaking or arcing over. To find out what its insulation resistance between the mains input and the DC output actually is, I used an insulation tester and using 500 volts DC test voltage it shows 195 megohms. That's not too bad. The unit is actually still working, delivering 12 volts. Sorry, somehow I can't find that video. Upon breaking it open, we see a pretty conventional power supply using mostly through-hole components. Even the bridge rectifier is made of individual diodes, which makes repairing easy were not for the liberal use of gunk. It looks as if the secondary winding of the transformer have some extra insulation, which is good. The underside reveals a really large gap between the primary and secondary. All in all, the MicroTalk 12 volt supply turns out to be a lot better than I thought. The usual Class Y noise suppression capacitor seems to be a genuine safety capacitor. I think the insulation resistance we measured is essentially across this capacitor. I found a possible Chinese datasheet of this capacitor and it's interesting. Apparently the insulation resistance should be at least 10 gig ohm while it can withstand 2600 volt RMS without damage. Now I measured the resistance to be only 200 meg, so maybe it's not the right datasheet, but judging from this one, the withstand voltage may be quite substantial and much higher than the 400 volts AC rating printed on the capacitor. If the capacitor in this power supply is similar, it would explain why it survived the testing. Moving on to number 2, the Philips shaver charger. For the output side, I use a piece of blank copper wire which simultaneously shortens the output and connects it to the high voltage. Running the tests again, starting from the lowest to the highest test voltage, only gives green lights. This Philips power supply passes all tests. The 1000 volts of the X-Tech wasn't enough to determine the insulation resistance between the mains input and the DC output. So here is my big guns insulation tester, a Unity UT513A. With 500 volts we just get over range, and the same with 1000 volts consistent with the X-Tech. But why stop here? Let's try 2500 volts. Now we're getting results. Nearly 64 gig ohms, quite a bit more than what the MicroTalk supply could muster. I tested the Philips and it was still working. Then I wanted to look inside, which was destructive because the case was welded shut. I have to say I'm impressed by the quality. The transformer, which is often the weak point in cheap power supplies, is extremely well done in keeping primary and secondary away from each other. Interestingly, there is no interference suppression Y capacitor bridging the primary and secondary sides, which probably explains the high insulation resistance. And look at the separation of the PCB, there's even a tracking slot to prevent any creepage. After seeing this, I'm no longer surprised that this thing can handle anything I could throw at it. Thumbs up for the Philips power supply. Number 3 is the battery capacitor tester. By now you're probably familiar with the setup of shorting the outputs together and then connecting them to the high voltage probe of the TM4700. And a similar picture starts to develop. I can run each test voltage and all I get is green pass lights. No problem for the battery capacity tester. What is its insulation resistance? Since I already had the Unity out, I decided to use that instead of the X-Tech right away, and indeed both 500 volts and 1000 volts failed to give any results. But similar to the Philips, 2500 volts was high enough for a reading, 6.25 gig ohm, not as good as the Philips, but second best so far. But contrary to the Philips, this unit has not survived the test and is now dead. No output and no blue light on the case. As with the other power supplies, opening is a destructive process. The inside looks quite conventional, no obvious damage. There is a resistor for inrush limiting, and since it's marked as F1 on the PCB it's probably fusible, but of course that resistor still tested okay. The gap between primary and secondary is not as wide as with the other power supplies, but still decent. I tested the bridge rectifier and all other diodes and all were okay. To test the Z diode at the output, I used a special tester and it showed 11.2 volts, which is okay. As a side effect, the test voltage activates the whole output circuit, so that part's still working. I suspect that somehow the switching IC did not like the high voltage and has died. On to the fourth item, the USB charger with a safety warning. Shorting the USB-C output is a bit tricky. In the end, I decided to use a USB-C to barrel plug converter I use for powering soldering irons, and then use a 2-wire lead with a barrel plug on one side and banana plugs on the other. Given its reputation, I'm really curious about this run. Starting with the lowest voltage, and it passes? I did not expect that. In fact, it passes all 3 tests with no problems. So what is its insulation resistance? 2500 volts. What? Still no result? Okay, we can go higher. 5000 volts. And now we're getting a result. 571 gig ohms, which tops everything we had so far. Almost 10 times more than the Philips had. How come it got that bad safety record? Maybe it's all burned out inside. But no, selecting 12 volt power delivery still works just fine. And so does 9 volts and 5 volts. Trying to get inside is actually quite easy, too easy in fact. While it resisted my attempts of using a spudger, a relatively moderate pull on the pins succeeds. I can totally see this happening accidentally by dropping the unit or possibly a knock against it while it was plugged into a tight wall socket. That part of the safety warning is certainly correct. Okay, we have a fuse or fusible resistor at the input, which is good. It is built rather compact, so I could imagine things can get quite toasty inside. At least it seems that the capacitors are rated for 105 degrees Celsius. The output of the transformer has extra insulation over it, which is nice. Of course, without taking the transformer apart, it's not possible to determine if that's just window dressing, but then it handled the TM4700 and 5000 volts of the Unity tester without issue. On the underside, the gap between the primary and secondary is huge. I really don't understand how it got its bad rating for electrical safety. It does not look that bad. It's of course possible that I've got a different batch from a different factory, so please don't take my result to mean that you should still use an SPTC78A if you have one. That leaves just unit number 5, the no-name power supply for Christmas lights from China. It is set up the usual way, with the output shortened and connected to the high voltage probe of the TM4700. Starting at the lowest voltage, and a fail. It does not pass. Let's try the highest setting as well. And it fails, of course. And the insulation resistance test measurement fails at just 500 volts. The Unity shows 0.0 megohm and cannot even sustain the 500 volts, just 104 volts. In fact, just a simple multimeter is needed to show that this has all of 4.7 megohm insulation resistance. And, repeating the functional test, there is no output voltage either. So, have I fried it? It opens very easy, and for a change, this is not a destructive process. Undoing one prominent screw is all that's needed. Good old insulation tape to prevent the plug contacts from touching things inside. And this is just a capacitor dropper, not a switch mode power supply. No wonder it has a low insulation resistance. Depending which way this is plugged in, all that stands between mains and DC output is a diode junction. I tested the rectifier and it was okay. In fact, the Z diode and the capacitor also tested okay. So why did this simple thing fail? Turns out one of the wires of the output cable had disconnected from the PCB due to excellent soldering in the factory. With the meter connected directly to the PCB, it is evident that the unit did not fail but is still producing normal output voltage. With all the candidates tested, what is the conclusion? My goal was to find out if reasonably modern Class 2 power supplies would survive being tested by this machine. From my batch of 5 quite diverse test candidates, 4 survived the test, which is more than I expected. The high survival rate may be because the designs, layouts and the components inside these power supplies are capable of handling much higher voltages than the relatively low tests modern PAT testing applies. Reputable companies probably add a safety margin into their products. Even the failed units did not cause a safety problem, it's just no longer working. All in all, the TM4700 did a good job. Those units that passed its test deserved it, and the totally unsafe Christmas light power supply was correctly failed. That is all very good, but frankly a bit underwhelming. Just like you, I was hoping for more spectacular failures, but there you go. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.